right, well, let's get moving along here with section 10.3, which deals with the chlorination of methane, the simplest possible organic molecule. And if we take methane and we subject it to chlorine and ultraviolet light, we end up producing methyl chloride, and we make some HCl in the process. So you can see that this is a substitution reaction, right? We're starting with the methane, and everybody here can draw the Lewis structure of methane, right? And what you're doing is you're substituting the hydrogen for a chlorine, right? That's all that's happening here. Well, let's take a look at the three stages of the mechanism, which is a radical mechanism. So the chlorination proceeds via a radical mechanism, and we're just going to take a look at all the stages. The first one is the initiation, right? When we treat the chlorine, Cl2, with light, it undergoes homolytic cleavage, and we end up with two chlorine radicals. So remember, we're starting it with something that is not a radical, right? Not a radical in the initiation, and then we're making radicals. Now, something that the book doesn't really go into a lot of detail about here is that we're putting the methane molecule with chlorine, and we're treating it with light. But not every chlorine molecule, not all of these are going to be converted into radicals. Okay, it's not like every chlorine molecule just gets blown apart and converted into radicals. Some of the chlorine molecules will be converted into chlorine radicals, and that's going to be important because we're going to need Cl2 later on in this mechanism. So after initiation, what happens next is propagation. The first step of the propagation is a hydrogen abstraction. It says that these two steps are self-sustaining. So we take that chlorine radical and it reacts with the methane molecule to produce a methyl radical and HCl. Now remember, I told you on the last slide that not all of the chlorine gets converted into chlorine radicals, right? We still have most of it as just molecular chlorine, Cl2. So the methyl radical can react with a molecule of chlorine to produce methyl chloride, our product, plus we make a new chlorine radical. So this is essentially a chain reaction, because if you tally up these two, if you add these two reactions together, what do you get canceling? Take a look. You have the methyl radical canceling on both sides, and you have the chlorine radical canceling on both sides. So overall, you get the actual reaction. You get methane plus chlorine is producing methyl chloride plus HCl, right? That's the reaction that we have way back here. Okay, that's this reaction here. So the sum of the two propagation steps gives you the overall reaction. But again, what I want to point out is that this is a self-sustaining sequence of events. Why? Because in the first step, you consume a chlorine radical, but in the next step, you produce a chlorine radical. So this keeps it going and going and going. Now, in order for the termination to occur, we have to have two radicals coming together, colliding or coupling, in order to make a non-radical, right? You see, everything over here is a radical, okay, and everything here is a non-radical. So what radicals are going to come together to make a non-radical? The answer is anything, okay? Termination is the simplest of all the steps for students to start out the mechanism of, because you can pick any two radicals in the reaction mixture, bring them together. You could make chlorine, you could make ethane, or you could make methyl chloride. But either way, if you bring any two radicals together to make a non-radical, that is considered a termination step. Done. Reaction over. So a little more about those two propagation steps. And I told you this on the last slide, that if you look at the sum of the propagation steps, it gives you the net reaction. So again, this is a chain reaction, because the product that's formed here, okay, is going to serve as a reactant later on, or for an earlier step in the mechanism, okay, which can be basically done over and over and over. Now, what's interesting about this reaction is that once you produce chloromethane, well, then it just keeps going, okay? So chloromethane, methyl chloride, either way, it's the same thing, okay? So it says polychlorination is actually difficult to prevent. Methyl chloride or chloromethane just keeps reacting with the halogen over and over and over, and you end up adding more and more chlorines. So then you could get to methylene chloride, then you can make chloroform, and then you can go all the way to carbon tetrachloride. So in order for this to occur, you would need, you need excess methane with respect to chlorine to get monochlorination as the main product, right? Otherwise, it's just going to keep going and going and going. Well, that's enough information for us to take a look at a problem. It says, be able to draw radical mechanisms like the one in Skill Builder 10.4. So make sure you take a look at that when you're studying. But I want us to take a look at a radical mechanism. It says, draw the radical mechanism for the following reaction. The chlorination of chloroform to produce carbon tetrachloride. So we're going to take chloroform. So that's CHCl3, so chloroform. And we're going to combine that with chlorine. Okay, we're going to treat that with light. And then we're going to end up with carbon tetrachloride, CCl4, plus HCl, right? That's the chlorination of chloroform to make carbon tetrachloride. Well, we're going to need more space to solve this problem. So let's go over to a blank document here. Let's give it the old college try. So what's going to happen first is initiation, isn't it? So the initiation is going to be the formation of a radical from a non-radical, right? So we need to take our chlorine and we're going to subject that to light, electromagnetic radiation, and that's going to break apart to form two chlorine radicals. Now remember, not all of the chlorine is going to be converted into chlorine radicals, but in this case, we're going to end up with a couple of radicals. So I'll just put two chlorine radicals. Now the propagation is two steps, right? The first one is a hydrogen abstraction. So hydrogen abstraction. So what happens there? What happens there is you have your chloroform molecule. So I'll write my CHCl3. I'm going to write out all the bonds explicitly. I don't really need to include all the lone pairs here, but that's going to react with a chlorine radical, again, in the hydrogen abstraction. And what's that going to do? It's going to abstract the hydrogen, right? So we're going to end up forming HCl and a CCl3 radical. So let's draw that out. We have our CCl3 radical, plus we formed HCl. So the next step is going to be the halogen abstraction. So halogen abstraction. Okay, so this is where our radical is going to react with Cl2. And again, I told you that not all of the chlorine, the Cl2, is going to be converted into radicals. Only some of these are going to form radicals. So let's draw the curved arrows for our halogen abstraction. Oops, I'm going to use a red arrow here like that. So we end up forming a chlorine radical plus carbon tetrachloride rather. So now we have CCl4 plus the chlorine radical. Okay, so we have our chlorine radical. And then for termination, again, you could draw any two radicals coming together. So termination, let's just draw, again, it could be anything. It could be, let's just draw two chlorine radicals meeting on the street. They come together, they produce a non-radical, and there you go. You end up with chlorine, and you're done, okay? Now again, if you want to double check your propagation steps, they have to combine, okay? These have to combine, there's a blue line here. They have to combine to give you the overall reaction. You see what's canceling here is we have the chlorine radical canceling, and then we have the CCl3 radical canceling, right? If you add this all together, you get chloroform plus Cl2 is producing carbon tetrachloride plus HCl. Sorry, I didn't see that question. So you would include Cl2 as a product. I'm not sure what the question is. Could you maybe put that in context for me? The termination step where you form, yes, Cl2 is the product. Yeah. And again, Warren, you could amend. I mean, you can combine anything. Okay, you could put these two radicals. You could put the CCl3 radical plus a chlorine radical. That's fine. You could put two CCl3 radicals coming together. That's cool. Okay, and I'll draw the arrows for them. Just give me a second here. Okay, but any one of these. Okay, you could draw this. You could draw any of these. So this would produce hexachloroethane, and this would produce carbon tetrachloride. All of these count as termination, okay? Any two radicals coming together. Okay, so again, we get the initiation step, the propagation step, or propagation steps, I should say, which are first a hydrogen abstraction, followed by a halogen abstraction, and then the termination, just draw any two radicals that you had in there coming together, and there you go, my friend, you're done. That's it. And again, if you want to check your propagation steps, they should tally up to give you the overall reaction, which is exactly right. All right. So let's talk a little bit more about this whole initiation of a radical, because the bond dissociation energy of chlorine is actually not that low. It's actually 243 kilojoules per mole that is required to break this bond. So there are other radical initiators that we can use. Let me show you some examples. Let's go back to the slide deck here and take a peek. So yeah, it says a radical initiator. It's better to use a radical initiator, and I think it's more common to use something that's got a weak bond that's going to break easier in the presence of heat or light. Again, you can just use a halide like chlorine or bromine. It can be done. I've done it myself. Okay, it's not a big deal, but sometimes you just need conditions where you need something that might be easier to break. So good examples are things like peroxides, alkyl peroxides, not hydrogen peroxide. So not H2O2, son of a gun. Okay, so H2O2, you can cross that off the list. Okay, and alkyl peroxide, right? ROOR. And you're like, hey, I remember that from anti-Markovnikov addition of HBr across the double bond. Yes, and we're going to bring that into the conversation today. But you see how the bond dissociation energy here is significantly lower than that of dichlorine. And if you want something that's even easier to break, you can use an acyl peroxide. So this is kind of a functional group I guess we haven't even seen before, an acyl peroxide. But that breaks even easier, right? The bond dissociation energy is even lower. And the reason why it's going to initiate the reaction most readily is because you end up with a radical that's resonance stabilized, right? And you could draw the curved arrows. They're in the textbook, okay? But you could draw the curved arrows to show the resonance contributor here. But the answer is to this question is the acyl peroxide, since lowest BDE, lowest bond dissociation energy. All right, so besides initiators, right, those are what kick off radical reactions. We can have radical inhibitors too, things that consume radicals. It says here that radical inhibitors, I'm just reading right off the slide, it says react with radicals to prevent the chain process from initiating or propagating. Some examples, it says here stabilized radicals and compounds that easily form stabilized radicals are good inhibitors. You remember from General Chemistry 1, and this might be taking you back in time a little bit, but I know that in your General Chemistry 1, you should have discussed oxygen. When you first learned to draw the Lewis structure of oxygen, you would have drawn it like that, O2. But then when you talk about the molecular orbitals and molecular orbital theory, you learn that oxygen is actually a diradical. Okay, it's got unpaired electrons, so it's attracted to a magnet, it's paramagnetic, and then you explain again it's because it's got unpaired electrons. So oxygen actually is an excellent consumer of radicals. It makes a good radical inhibitor, right? Because if it sees another radical, right, let's say there's a radical that you don't want in your reaction mixture, well, oxygen is just going to consume that. Or let's say you're doing a reaction and you want to have a radical. Well, if there's oxygen in your reaction mixture, it's just going to get rid of it. Okay, it consumes it. So normally when we do all these beautiful radical reactions, we try to avoid having oxygen around. Another one is hydroquinone. So hydroquinone will also react with two radicals. And the reason why is you can do a hydrogen abstraction with either of these over here to produce a resonance stabilized radical. I think I have it on the next slide. But again, you know, if you try to do a radical reaction in the presence of oxygen, it's usually sluggish because it just starts consuming all your radicals. And if you're wondering, well, how do you get rid of oxygen? Isn't that in the atmosphere? Yeah, it is. But there's ways that chemists have to mitigate the amount of oxygen that reactions are exposed to. But check out hydroquinone, what this can do. If it sees a radical, it does a hydrogen abstraction. You abstract the hydrogen from the hydroquinone, you end up with a radical that's resonance stabilized, right? You could start by drawing, you could practice drawing your radical arrows like that, okay? But look at this. You've got another hydrogen. It can do another hydrogen abstraction, and then you end up with this fully conjugated molecule here, which is called benzoquinone. So again, hydroquinone is a great kind of radical scavenger, or it consumes radicals. Anyhow, and we call that a radical inhibitor. All right, so that covers section 10.3. Now I want to talk to you about halogenation thermodynamics, okay? I promise that if you follow along with me here, this section is very reasonable.
And this is a waste.
Okay, thanks, buddy. Yeah. Dad's teaching the class. All right. Yeah, so halogenation thermodynamics, this is what's going to help us to understand why chlorination and bromination of alkanes is reasonable. Okay, bromination is preferred by most organic chemists, and I'll explain why in a little bit. And it will also explain why fluorination and iodination are kind of useless for different reasons. Okay, so let's take it right back to delta G, right? Gibbs free energy. If we want to determine whether a process is favored, right, if a reaction is going to work or not, we have to determine the sign of delta G, Gibbs free energy, which we have the formula here that Gibbs free energy is equal to the enthalpy plus the entropy term here, which they factored in is negative T delta S, which the textbook likes to do. But anyhow, we know that if the sign of delta G is negative, our reaction is going to be spontaneous. It's going to happen. It's going to occur. If delta G is positive, well, then the reaction isn't spontaneous. It's not going to occur. So let's talk about the entropy term first, okay? All of this over here. Negative T multiplied by delta S. Well, if you just look at the change in entropy, the entropy term is essentially negligible for looking at halogenation reactions. The reason why is because you're starting it with two molecules, your alkane plus your halogen, and you're ending up with a haloalkane plus some kind of HCl, HBr, whatever, okay? And so the entropy term, since there's no change in the number of reactants and products, you're starting with two molecules and ending up with two molecules, you can essentially cancel this term out. Okay, so let's see here. We'll cancel this term out. And so what we end up seeing is that Gibbs free energy is closely equal to the change in enthalpy. Okay, so all we're going to have to do is evaluate the change in enthalpy in order for us to study the thermodynamics of halogenation. And what's change in enthalpy? What's delta H related to? Well, if you go back to chapter 6, what did we relate changes in enthalpy to for a reaction? Bond dissociation energies. So let's take a look at some bond dissociation energies. And let's take a look at the delta H, which again is directly related to the delta G for the halogenation of methane. So here we have the bond dissociation energies for the halogenation of methane, either using fluorine, so F2, chlorine, Cl2, bromine, Br2, and iodine, I2, right? We have all of these different values here for bond dissociation energy. So let me just show you how to calculate one of them. And again, this is a review of chapter 6. So if we wanted to calculate the delta H of the reaction, okay, the delta H of the reaction for fluorination, okay, so fluorination, okay? Well, remember that to break these bonds, right, you want to break this carbon-hydrogen bond, you want to break the dihalogen bond, that's going to cost you energy, isn't it? Right, that's energy that's got to go in. So we're going to say energy required, okay? So how much energy is it going to take to break the bond? 435 kilojoules per mole. And we're also going to have to break the F2 molecule, which is going to cost us 159 kilojoules per mole. I'll throw the units in at the end. Now, energy is going to be released when we form the carbon-halogen bond and the hydrogen-halogen bond. So we're going to say here, energy released. And so we can say the delta H of our reaction is going to equal the sum of the energy required, subtract the amount of energy released, which is 234 plus 297. All of these are in kilojoules per mole. And again, we're just calculating it for fluorination here. And what you end up with is an exothermic reaction. The delta H is negative 431. And I know there's not a lot of room here, kilojoules per mole. But remember, we saw that delta G is approximately equal to the delta H. And so what does that tell you? That fluorination is a very exothermic reaction, right? It releases a total of 431 kilojoules per mole of energy. And so if we compare that to the delta H of chlorination, bromination, and iodination, you see that fluorination is by far the most exothermic of them all. In fact, it's too exothermic, okay? It's too exothermic. So exothermic that it could cause something like an explosion. Now, as an organic chemist, we generally frown upon things like explosions in the lab. Now, if you take a look at the other values, the delta H of chlorination and bromination, they're both negative, aren't they? So what does that mean? Since delta H is approximately equal to the change in Gibbs free energy, that means that these are spontaneous processes as well, right? Just to summarize, right, all three of these are spontaneous, okay? Spontaneous reactions. However, it just happens that the level of spontaneity, maybe, of the fluorination is too great. It's so exothermic that it's useless, okay? Now, if we look at the delta H of iodination, what do you notice right away? It's positive. So that means your delta G is positive, so that's not a spontaneous reaction. And so that renders iodination, this process is useless, okay? If it's not spontaneous, it's not very helpful for us, is it? So we'll put here, not spontaneous, and therefore kind of useless, okay? So what have we discovered? We've discovered that fluorination is too dang violent, okay? It's so exothermic that it's pretty much useless. And we've discovered that iodination is endothermic, therefore it's an endergonic process, and it's not going to occur. So that means that what are we interested in, right? As organic chemists, we're interested in useful reactions, aren't we? Absolutely. So that means that only halogenation with chlorine and bromine are going to be useful. Okay, well, that sounds pretty neat. Well, now what we're going to do is we're going to look at the difference between chlorination and bromination, because I'm here to tell you, my friends, that once we get to the end of this section, you're going to realize that bromination is more useful. Chlorination is useful. It's got its place. But it's not nearly as useful as bromination. And I'm going to explain the reason why that is. And in order for us to understand that, we're going to take a look at the propagation steps of the halogenation of ethane. Okay, so this is an ethane molecule here, right? CH3. Okay, and we're going to take a look at the individual propagation steps, okay, of the halogenation of ethane. So the first step, remember, is a hydrogen abstraction. So this is our hydrogen abstraction. And the second step is the halogen abstraction. So halogen abstraction. Now let's compare the two for chlorination and bromination of ethane. All right, look at the first step, the hydrogen abstraction. Well, if you look at the change in enthalpy of the hydrogen abstraction for chlorination, you see that it is an exothermic process. Hey, it's spontaneous, right? Because we said that the delta H is going to be pretty much equal to the delta G. So, hey, it's a spontaneous process, right? Well, maybe I shouldn't say spontaneous process. Let me back that up. Let me put it just in terms of delta H. We'll say that the hydrogen abstraction with chlorine, the chlorine radical, we'll say it's exothermic. Okay, we'll just leave it at that. It's exothermic. Whereas the hydrogen abstraction with the bromine radical is endothermic. Okay, so there's a difference here. Now, if we look at the second step for both of them, which is the halogen abstraction, you see that the halogen abstraction for both of them is an exothermic process. Okay, now I told you this many times that when you tally up the two steps of the propagation, right, when you tally both of these up, what can you do? You can cancel this, okay? You can cancel this, and then overall you get ethane, okay, plus your halogen gives you the haloethane plus H halogen, okay? So the net reaction, in order to determine the change in H, or the delta H, or the change in enthalpy for the overall process, which is this process here, I have to tally up the change in delta H for both of these steps. Now, if you do it for the chlorination, what do you see? Minus 21 plus negative 26 gives you negative 117. So the whole process is exothermic. Good. It's going to be a spontaneous process. Even though the first step here is endothermic, if you tally up both of them, you end up with a negative overall change in enthalpy. So what does that tell you? It tells you that bromination is also an exothermic process, right? The delta G is negative. So both of these are spontaneous processes, right? Just the difference is this. The only difference is that the first step, the hydrogen abstraction in bromination, is an endothermic process. And this is why, or this is how we're going to rationalize that bromination is a more useful reaction. So let me explain that to you by looking at a reaction coordinate diagram. Okay, so here is the reaction coordinate diagram for the hydrogen abstraction followed by the halogen abstraction for chlorination and bromination of the ethane molecule. Okay, so again, the first step, this is the hydrogen abstraction, okay? And this is the hydrogen abstraction here, okay? This is the halogen abstraction. I'll call it X because we use X to represent a halogen in organic chemistry. Now, the rate determining step in both of these is the halogen abstraction, right? This is my rate determining step, the first one, and this is my rate determining step here. Well, if the activation energy for chlorination is much lower for my rate determining step, that means that this is going to be much faster, isn't it? Right? If the first step, which is the rate determining step, is a lower activation energy, we know that activation energy is directly related to the speed of the reaction, right? The lower the activation energy, the faster the reaction. Okay? So bromination is much slower because it has a much higher activation energy for the rate determining step. However, what this means, what the conclusion that we can draw though, is that bromination is going to be more selective. And that's going to be based off of the Hammond postulate. And in order for us to understand this completely, we have to look at the transition state. So we have to examine the first step even closer. Okay? And we're going to do that in a couple of seconds, but I want to show you something interesting. Okay? Let's say you have propane. Okay, this is just a propane molecule, right? CH3, CH2, CH3. Well, how many types of protons are there in propane? There's two types, right? There's the two hydrogen atoms that are highlighted in orange. Those are in the methylene. And then you have 6 hydrogen atoms on the 2 methyl groups. Well, if you wanted to do a monohalogenation on that, okay, whether it was chlorination or bromination, you know, just in terms of statistics, you have 3 times the amount of hydrogens on the methyl groups than you do on the methylenes, right? The ratio is 6 to 2, which is the same thing as 3 to 1 or 75 to 25, whatever, you know. So you would think about it that if you were to try to chlorinate propane just based off of the number of protons in orange and the number of protons in green, you would assume, you know, I would assume that the ratio would be, you know, a 3 to 1. Sorry, 3 to 1 for here to here. Okay, but what you actually see is if you do this reaction, check it out, you actually end up with mostly halogenation at the methylene position, okay, and you only end up with 40% halogenation. Did I say methylation when I meant halogenation? At the methyl position, okay? So you get something that's totally non-intuitive, right? Most of the chlorines actually end up on the methylene, okay? And what happens is the reason why it's based off of that first step. So what you see in this reaction coordinate right here, okay, what you're looking at in this picture, let's back up. It's this right here, okay? It's just to zoom in. So now we're going to zoom in on what's in this box, and we're going to take a look at the activation energies and the radicals that are produced when we do the hydrogen abstraction to make these two products. So you see that the difference in activation energy of forming the primary versus the secondary radical isn't all that great, is it? Now you see that the activation energy for the formation of the secondary radical is lower, right? So therefore that's going to occur faster and you end up with a more stable radical. So that explains this first step, this hydrogen abstraction explains why we get more chlorines in the secondary position or in the methylene position than we do where the methyl group is, okay? Or what? So I should say we get more 2-chloropropane than we do 1-chloropropane would be the proper way of saying it. Okay, give me a thumbs up if you follow me thus far. We're just looking at the hydrogen abstraction step of chlorination. And the lower activation energy to produce the secondary radical explains why we get, something that's maybe not intuitive right away. Okay, that most of our product is the 2-chloropropane, and we end up with less of the 1-chloropropane. Okay, I'm going kind of slow, and it's because I want it to all come together. I don't want to throw you for a loop or anything like that. So check this out. Okay, are you ready for this? If you try the same experiment as this, but you replace the chlorine with bromine, check it out. Look what happens then. The bromination is slower, okay, because the first step was endothermic, but check it out. Now you end up with 97% 2-bromopropane and only a tiny bit of 1-bromopropane, okay? Now, the fact that this reaction is way more regioselective can be explained using the Hammond postulate. All right, the Hammond postulate is not meant to be a complicated postulate or anything. What we're going to do now, and I'm going to back up again because I want to make sure you follow me. Now we're going to compare the hydrogen abstraction of the chlorination to the hydrogen abstraction of the bromination. Okay, so let's look. I have it right here. Okay, now, since the hydrogen abstraction of the chlorination process was an exothermic process, right? The transition state is going to more closely resemble the reactants, right? That's the Hammond postulate, okay? If the transition state is closer in energy to the reactants, it's going to more closely resemble the reactants. But if you look at the first step, the hydrogen abstraction during the bromination process, you see, look, now it's the opposite. The transition state more closely resembles the intermediates. What's the intermediate? The intermediate is a radical. That's starting to come together. So the chlorination transition state more closely resembles the reactants, whereas the bromination transition state more closely resembles the, it shouldn't say the products, it should actually say the intermediates, okay, the radical. So what does that mean? Okay, that means that at the transition state of chlorination, the bond between the carbon and the hydrogen has only just begun to break. It doesn't have very much radical character, does it? Whereas in the bromination process, the transition state much more closely resembles the radical, right? Because the intermediate is the radical. And so at the transition state, the carbon-hydrogen bond is mostly broken. What does that mean? That means that the transition state, the carbon here has much more radical character. Well, what do we know about the stability of radicals? Right? If the transition state much more closely resembles an actual radical for bromination, it's going to be much more affected by the stability of a radical, isn't it? Okay. Now, if you go back here and you compare the stability of a secondary radical versus a primary radical, we know that a secondary is more stable. But again, since the transition state of bromination much more closely resembles this, it's going to be much more affected by the stability of a radical, right? The transition state of the chlorine has partial radical character, okay, but much less. So it's not going to be affected by radical stability nearly as much, not even close. Okay, so for bromination, I'm just reading off the slide. It says the stability of the transition state largely depends on the stability of the resulting radical or carbon radical, whereas in chlorination, the stability of the transition state doesn't really depend on that at all, okay, or very little, okay? And so that is why bromination is so much more discriminant, whereas chlorination is kind of wild, okay? It's much less discriminant. You saw how we ended up with a mixture. So look at this. Now, these are just the first steps. Again, we're just talking about hydrogen abstraction. If you compare the difference in the energies of the transition states for chlorination, look at the difference in energies of the transition states for chlorination. Very little difference because they have very little radical character. So that means are we going to get some discrimination and chlorination? Will we mostly, produce a tertiary radical? Of course, but the discrimination or the discrimination is going to be much less than if you look at the first step for the hydrogen abstraction, right, of bromination. The difference in energies of the transition states are huge here, right? Look at the gap here is really tiny. The gap here is gigantic. So that is why bromination is going to be much more selective for a tertiary radical versus a secondary versus a primary. Again, they're both selective for a tertiary, right? Tertiary radicals are more stable, okay? But again, the bromination process is going to be much more selective. All right? Give me a thumbs up if you follow me on that. Because if you understand even a little bit of what I said, you understand. Or if you understand most of what I said, you understand, something that is really important. Okay? Now, if I only had 30 seconds to teach this to you, if somebody said, Mr. Dion, I'm going to give you 1 minute, and change, and you need to teach this to your students, this is what I'd tell you. I'd tell you what's on this slide right here. I'd say, if you have some kind of alkane, you've got a carbon-hydrogen bond that if you broke would produce a tertiary radical, okay, versus you've got another kind of carbon-hydrogen bond that if you broke that, you'd end up with a primary radical. You'd say, well, if you did chlorination, you'd end up with a mixture of both products that result from the primary radical and the tertiary. It would favor the tertiary, yes, but if you did bromination, baby, you'd probably get mostly just the bromination at the position that yields the tertiary halide. Why? Because this pathway is so much more dependent on radical stability, and a tertiary radical is much more stable than a primary radical, okay? So there you go. This has much greater synthetic utility. I mean, come on, anything that will give me 100% yield, I'll take it. If I can get 100% yield, I'm going to run with that. Okay, if I end up with something that's a 35-65 mixture, good gravy. Then you got to purify that, then it turns into a thing, and it just gets really annoying. So there you have it. So if we look at, again, the regioselectivity for fluorination versus chlorination for bromination, and if you're like, Mr. Dion, I thought you said fluorination was useless. It is, okay? It's so fast that it's useless, but this table is just a comparison, just so you can see. If you look at the discrimination in fluorination, since that first step is so dang exothermic, okay, that there's hardly any discrimination at all, okay? It's almost 1 to 1 to 1. Yeah, there's a little bit, in favor of tertiary, but not much. Chlorination is a little bit better, but then if you look at bromination, it's really useful because it's so selective. So with all that in mind, if you're wondering, what are you going to ask me? You're going to ask me about transition states and the Hammond postulate. That might be worth the value of one multiple choice question or something that I want you to understand the concept. I'm not going to be like, here's a blank sheet of paper, write me an essay about it or anything like that. I want you to understand the concept, but here's what you really need to know as an organic chemistry 1 student. If I had, one kind of skill that I want you to take away from this, it says predict the major product. What's going to happen if you treat this with radical bromination conditions? So we'll say bromine and light. What the heck is going to happen? I'm going to label a couple of protons here. Let's say we get this proton in black. Let's say we get this proton in blue. Let's say we have this proton in red. And let's say we have, I don't know, let's take this one in green. I don't know. Could anybody tell me where bromination is going to occur? Which proton? Yes, absolutely. 100%. Okay. So that was a lot of me talking for something that I knew you would get pretty quickly. It's going to be the one in red, isn't it? Because that's the one that's going to produce the most stable radical. If you don't believe me, let's draw it. It's not asking us to draw the intermediate, but it's kind of fun to do that. So let's pencil that intermediate in here. There you go. It's a tertiary radical. And then ultimately, we're going to end up with the halogen abstraction occurring. Yes, absolutely. My students are all 100% correct. And we're going to end up with this. And that's it, my friend. Okay. Next one, I bet you can all see right away that you're going to get the halogenation occurring here. The only place where we have a tertiary carbon, and that would be 100% correct in assuming that. So bromine and light, and you would end up with this. Oops, I'm missing a carbon. And you end up with the bromine here. Look, let me tell you one more thing here. And it does come up later in the book, But I want to share one more thing with you, okay? Just to kind of cement it in your mind. If you're wondering, like you spent a lot of time talking about chlorination, Mr. Dion, are we just going to throw that out? The only time chlorination is going to be useful, really, the only time that I would expect you to use it is, let's say you had cyclohexane and you wanted to halogenate it. If you used chlorine and light, well, there's only one type of proton in cyclohexane anyway. So that would be useful. You'd end up with this, but that's the only possible product. There's no other regioisomer. Okay, so anytime that you could end up with regioisomers, you would always use bromine and light. Okay, here we go. We got time to talk about stereochemistry. Let's keep going here, because I think that everybody was following me when we talked about the identity, or the structure rather, of a carbon radical, right? We said that it was trigonal planar, or it was such a shallow pyramid that was so rapidly interconverting that we could treat it as a trigonal planar species. So the halogenation of butane or more complex alkanes can form a chiral center. Okay, so if we treat this with chlorine, okay, well, chlorination is not nearly as regioselective as bromination, so we're going to end up forming a couple of radicals. But if we form the secondary radical, right, which would be this, okay, well, remember, we can treat this as being trigonal planar. So that means when the halogen abstraction occurs in the next step to make this compound, it can occur from either face of the molecule, right? So you end up with a racemic mixture of 2-chlorobutane, and then of course this has no chiral centers, 1-chlorobutane. So again, this is going right back to the first section that we looked at this morning, right? The structure of a free radical. And we said that it can be treated as if it is trigonal planar. Let's keep going. So since it's trigonal planar, again, that halogen abstraction can occur from either face of the molecule, right? You end up making this radical, and I'm just redrawing what I had a couple of slides ago, okay? And that can either make the S2-chlorobutane, or it can make the R2-chlorobutane. And then, of course, if you produce the primary radical, which is going to look like this, okay, then that's going to make 1-chlorobutane. All right. And again, I mean, you don't have to draw any curved arrows to try to represent chlorination from either face of the molecule, but, you could say it's either coming from this side, like this, or you could say, well, it's coming from the back, and I could draw the back, maybe like this or something, okay, which isn't really a thing, but sometimes organic chemists do that to make themselves feel better. But anyhow, you end up with a racemic mixture. All right, there you go. So in terms of stereochemistry, it's not stereoselective, really. What else? If the halogenation of S3-methylhexane, the chirality center is the most reactive carbon in the whole dang molecule, right? You know that this hydrogen that I'm drawing in red right now is the one that's going to produce the most stable radical. So this is one of those examples where, let's say you worked super hard to make this chiral center, to make S3-methylhexane, then you brominate it. Well, yeah, you're going to be regioselective, but now you've got a racemic mixture of R and S, okay? So that would be a victory in terms of regioselectivity, but a loss in terms of stereochemistry. I don't know. Anyhow, there you go. But that's just the kind of things that an organic chemist has to take into consideration, right? She or he has to always be on their toes and thinking about, what could go wrong now? If something can go wrong, it will. It's Murphy's Law, right? Anyhow, let's take a look at so a question here where we consider stereochemical outcomes of radical bromination. So radical bromination, we're just going to take the molecule, we're going to treat it with bromine and light. I think that everybody would recognize by now that this is going to be the weakest carbon-hydrogen bond. If that gets broken, right, in a hydrogen abstraction, homolytically, we take this beautiful, tasty chiral center and we convert it into something that is trigonal planar. So we destroy the chirality. So now, when the bromination occurs, it's going to occur from either face of the molecule, and you're going to end up with this. So you're going to end up with my gem dimethyl here. We'll put the bromine here and the methyl group here, and then you're going to end up with the enantiomer as well. So you end up with a racemic mixture. All right, let's try the next one. So if we treat this again with bromine and we shine some light on it, hopefully you can all see that this is going to be the weakest carbon-hydrogen bond. Why? Because it's going to form a tertiary radical, but we didn't touch this stereocenter over here. Okay, well that's kind of neat. So now if the bromine can be attached to either face of the molecule where that radical is, we're going to end up with two compounds. And what's the relationship between those two compounds going to be? Let's see. Let's draw this like this. Put our tert-butyl group in. And then this methyl. I'm just going to copy this and paste this just to save myself a little bit of time. There we go. So we're going to end up with the bromine being up and the bromine being down. Could anybody tell me what the relationship between these two molecules is? These two molecules that I'm putting in this green box. What would the relationship between these two compounds be? Yeah, thanks, Mackenzie. Absolutely. Yep. Everybody's right. Hey, you guys are fast. They're diastereomers. Now, this is something that is mentioned in our book. I've never asked a question about it. However, I have not seen it in an ACS, but I did see it in an MCAT exam. So it is covered in our book. I want to show you something kind of cool here. Check this out. Now, in the first example, okay, this radical, if you look at this carbon right here, it's got two methyl groups on it. So when the halogen abstraction occurs, right, and I'll just draw the mechanism of it here. I mean, it's going to go to either face. Oops. So here's a fish hook like this. Son of a gun. There we go. So there you go. It's going to be indiscriminate for either face of the molecule because there's no chiral centers in this molecule. So that's why you end up with a racemic mixture. Okay, you end up with a 50-50 mixture of these two compounds. This compound plus the enantiomer. Now check this out. Since you have a radical here, but you've got a stereocenter in the molecule, well, the two faces of the molecule aren't the same, are they? Right? This side has got a T-butyl coming out towards the top, and here you got a little old methyl poking in the back. So if I had to guess, and I'm really just guessing here, I would guess that this would be the major product, okay, and that this would be a minor product. Why? Because a bromine is bigger than a methyl, and here the bromine is trans to that big bulky group, whereas here the bromine is cis to that big bulky group. Now, I could be wrong about the major or the minor, but the take home, so if you're like, well, if you're wrong, then what are you showing? What are you telling me? What I'm telling you is this, is that these two diastereomers are not going to be formed in an equal amount. You're not going to get a 50-50 mixture. One of them will predominate, okay? And again, the reason why is because the intermediate, the radical, has a chiral center in it. And so there's no way that the bromination is going to occur 50-50 on either side if these two groups are so different in their size. Okay, give me a thumbs up if just the concept makes sense, because I'm never going to ask you to predict which diastereomer would predominate. It's more just knowing that in this case, you would not have a 50-50 mixture. All right, there you go. Kind of a cool concept. Something that's not covered a lot in organic chemistry for non-majors. It's looked at more in organic chemistry for majors, but anyhow, some more food for thought there.